Hello everyone, welcome to Circuits and Electronics Classmate Contest 3. My name is Marco Antonio Vizcarra and today I will show you my project. The name of my project is Digital Dimmer. What is a dimmer? Basically, a dimmer is an electronic system to regulate intensity. In this case, to regulate the intensity from a light bulb. Okay, let's start. What do we want to do? As we said before, we want to control the intensity from a light bulb. Usually, the input voltage from a light bulb is 120 RMS voltage. That's the voltage that we get from the AC adapter from a house, for example. If we graphed the input signal from the AC adapter, the AC signal, it will have the form of a sine wave. By definition, the RMS voltage from a sine wave is the peak voltage divided square root of 2. There is some mathematical procedure to know this formula, but we won't go into detail about this. So if the RMS voltage from a sine wave equals to 120 volts, the peak voltage will be equal to the RMS voltage times square root of 2. Therefore, the peak voltage will be equal to 169.7 volts. Also, it's important to note that the AC signal has a frequency of 60 Hz. So the period of the signal is 1 divided frequency, so the period is 16.66 milliseconds. In order to control the intensity from the light bulb, we don't want to have the complete sine wave on the light bulb. We just want to have part of the sine wave on the light bulb. If after each semi-cycle starts, we wait some delay, and if after the delay the signal is available on the light bulb, we'll be able to control the intensity from the light bulb. The higher D is, the lower the intensity is. By intuition, because if the delay is higher, the voltage on the light bulb will be lower, as we can see in the graph. Here we can see a general diagram of our system. We have as an input the AC voltage from the AC adapter, and as an output the light bulb. We also have an input named control, which will allow us to regulate the intensity from the light bulb. In other words, it will allow us to control how big or how small the delay is. Now we know what we want to do, but how we will do it? Let's start with the design of the system. Let's start by drawing a block diagram of our system. Since we want to have digital control, we will use a digital controller. An input of the controller will be the zero crossing detector circuit. We will explain more details about this circuit later. We also have something named control, which will indicate how much intensity we want to have on the light bulb, or how big or how small the delay is, as we said before. An output from the controller will be a trigger signal, which will go to a trigger circuit. Basically, the trigger circuit will control how much current we'll have on the light bulb, or how much voltage we'll have on the light bulb. And finally, after the trigger circuit, we have the light bulb. Let's start by designing our zero crossing detector circuit. First, we need a rectifier circuit. We can create a rectifier with a special configuration of diodes, as we can see in the diagram. Each diode consumes between 0.5 and 0.7 volts, but since the input voltage is much greater than the voltage of the diode, we can consider the voltage of the diode 0 volts. For our calculations, we can ignore the voltage of the diode. We can consider it 0 volts. You can see how the current is flowing during the positive semicycle. Just follow the red arrows. Also, you can see how the current is flowing during the negative semicycle. Notice that during the positive semicycle and during the negative semicycle, the current through R is always in the same direction. This is the objective of the rectifier. If we graph the voltage through R, we'll see just positive values. We'll see the absolute value of the sine wave. Now, let's see if our rectifier is working correctly. First, let's measure the input signal. Here we can see the sine wave, which has a frequency of 60 Hz and a peak voltage of 168 volts. Now let's measure the output from our rectifier. We need to know if it is working correctly. Great, we can see the signal rectified. We are seeing the absolute value of the sine wave. So now we know that our rectifier is working correctly. To continue designing our zero-crossing detector circuit, we need a transistor. In this case, we will use a BJT transistor, which has a base B, a current C, and a emitter E. If we graph the behavior of this transistor, we can compare the voltage through collector emitter and the current through collector. It has two regions, which is the cutoff region, where the current through collector is 0 amps, and the saturation region, where the current through collector emitter is 0 volts. It has another region, but we won't go in detail about the other region. We wanted to work on these two regions. If we have the following circuit with an input voltage at the base from the transistor and a resistor between VCC and the collector, we can calculate some values. If we are in the saturation region, we know that the V out or voltage through collector emitter will be equal to 0, and then the current through the resistor will be VCC minus V out divided by RC, which equals to VCC divided by RC. On the other hand, if we are in the cutoff region, we know that the current through collector will be equal to 0. Then we can note that the V out or voltage through collector emitter will be equal to VCC. Now we have to decide what kind of transistor we will use. I decided to use the 4N2540 transistor. This is a nice transistor because there is no physical connection between the base and the collector emitter. There is no physical connection, so we can isolate two parts of the circuit. We can isolate the AC part of the circuit and the digital part of the circuit. So if one part of the circuit is damaged, the other part of the circuit won't be affected. This is absolutely nice. If we check the datasheet from this phototransistor, we know that we are in the cut-off region when current through R1 is equal to 0. And when current through R1 is equal to 0, the Vout or voltage through collector emitter will be equal to VCC. As a consequence, current through R2 will be equal to 0. And we know that we are in the saturation region when the current through R1 is greater than 0. Why greater than 0? Because we require small current to get into saturation region. So we'll consider it just greater than 0, because the input signal will be the AC signal, which is a really big voltage. So it will go into saturation region really fast. And when we are in saturation region, the Vout will be equal to 0 and the current through collector will be equal to VCC divided by R2. Now we can see the final diagram of the zero crossing detector circuit. We have a resistor R1 of 47 kilo ohms. The value of R1 is a high value because we need small current to get into saturation region. Also, we can consider the value consumed by the LED is about 1 volt. We can verify these values by checking the datasheet. Now we know the value of R1, but we also need to know the power consumed by R1. So the power consumed by R1 is equals to the peak voltage of the input signal minus the voltage consumed by the LED squared divided by R1. So the power consumed by R1, the maximum power consumed by R1, because the input signal is a sine wave, will be equal to 0.605 watts. So we choose a resistor R1 of 1 watt, which is greater than 0.605 watts. Now we choose a resistor R2 of 10 kilo ohms because we don't need big current on the Vout, we just need the voltage. So the maximum power consumed by R2 will be VCC times VCC divided by R2. So the maximum power consumed will be 2.5 milliwatts. So we choose a resistor R2 of a quarter of watt. Now we can see how the output signal from the zero crossing detector circuit should be. The input signal is the AC signal and the output signal is the Vout voltage. When the Vout voltage is 0, we are in the saturation region, but when the Vout is VCC, we are in the cut-off region. We are in the cut-off region when the input signal is near to 0. So this is how we are detecting each time the input signal is crossing through 0. This is how we create the zero crossing detector circuit. Now let's measure the signal, the output signal from the zero crossing detector circuit. You can see in the oscilloscope the signal. You can see here that I'm taking the signal from the resistor connected to the collector from the phototransistor. You can see the signal on the oscilloscope. Can you see? Can you see the resistor and the phototransistor? Okay. this signal goes to another device, and now let's check the signal in detail. Here you can have the signal. You can see the signal. It has a frequency of 120 Hz. That's what we are expecting to see, in a maximum value of 5 volts, since VCC is equal to 5 volts. Now, since we want to isolate two impedances from one circuit and from another circuit, we need to create a voltage follower. We can create this circuit by using an UA741 op-amp. Here you can see in the diagram how the output signal from the zero crossing detector circuit is connected to the positive input from the op-amp, and the output from the op-amp is connected to the controller. This is how we can isolate the impedance from the zero crossing detector circuit and the impedance from the controller, just by using a voltage follower. Now let's measure the input signal and the output signal from the voltage follower circuit. Both signals should be the same, since it is a voltage follower. Let's verify this. The yellow signal is the input and the green signal is the output. They are almost the same. We can see that the output signal is a little bit lower than the input signal. This is because the VCC voltage from the op-amp should be higher if we want the Vout signal to be higher, but they are almost the same. Now let's create the trigger part of the circuit. Remember that the trigger part will control how much intensity we have on the light bulb. In order to do this, we'll use the device named MOC3010. This device will also isolate two parts of the circuits, the digital part and the AC part. Basically, this device is like a switch. When the current through the LED is high, we will have like a closed switch on the output. Now let's calculate the current through R3. If we consider the voltage consumed by the LED is about 1 volt, the current through R3 is equal to 5 volts, which is the output of the controller, minus 1 volt, which is the voltage consumed by the LED, divided by R3. So the current through R3 is equal to 18.18 milliamps. Let's check the datasheet. According to the datasheet, the minimum current through the LED to activate the output is 10 milliamps, and we have 18 milliamps, so we are okay with the input current. When the controller activates the output of the device MOC3010, this device will activate a device named triac. This will be activated but having some current at the gate, some current named IG. Let's do a quick explanation of what a triac is. A diode, a perfect diode, is like a short circuit when current goes through positive to negative. But when current goes from negative to positive, the diode is like an open switch. In a triac, when the gate is activated, current could go in both directions. An ideal triac is like a short circuit when the gate is activated. by some current IG. But when the gate is not activated, the ideal triac is like an open switch. Here we can see the datasheet from the triac we are using. We can see that we need small current to activate the gate, and we can see that it supports a lot of current through it. It supports a lot of power. That's why we are using this triac to activate the light bulb. So basically, the controller will say what part of the signal of the sine wave will be on the light bulb. This is how we are going to control its intensity. This is the microcontroller MITx 6.002x that we are going to use. This is the controller that will receive the signal from the zero crossing detector signal, and we are going to define how much delay we are going to have. It means that we are going to decide how much intensity we will have on the light bulb, and the controller will trigger the trigger circuit to control the intensity from the light bulb. Now we are going to measure the trigger signal from the microcontroller. The trigger signal which activates the triac. Here we can see the signal. There are some pulses to activate the triac. If we move the time scale, we can see the pulse. It's a squared pulse. So this is the signal that activates the triac. Now what we are going to do, we will develop the firmware for the microcontroller. We are using the microcontroller we set. We're having a clock frequency of 20 MHz. Here you can see the code. I won't into detail about the code, but here you can see the code. We compile the code, everything. Now we need to download it into the microcontroller. Okay, we select the file, the firmware, we configure the microcontroller, we just configure it, and now we download it into the microcontroller, and let's wait. Okay, now it's ready. Okay, here we are downloading the firmware into the microcontroller. Okay, now here we have the controller, and it's ready to test it. Here you can see the final circuit is with the zero crossing detector circuit, the controller, and the trigger circuit, finally the triac. Let's test it and let's see how it works. Okay, before we test our circuit, let's make sure that we are having the right VCC values. We are having plus 5 volts and minus 5 volts for the op-amp. Okay, let's turn on the power supply and let's measure the voltages. Okay, here you can see the circuit. Okay, and we have a VCC of 4.98 volts, which is near to 5 volts, right? And the VCC is okay. Now let's measure the minus VCC. Okay, it's minus 5.01 volts, which is correct. Okay, the voltages are working correctly, and here you can see a LED indicator for VCC. Okay, here we have the final circuit with the light bulb connected. You can see two buttons connected to the controller. One button is to increase the intensity, and the other one is to decrease the intensity from the light bulb. Here you have the light bulb connected to the circuit, specifically connected to the triac. Everything looks in place. Okay, let's turn on the power supplies. Okay, minus VCC plus VCC. Okay, here you can see the initial signal. We can see the delay is peak and the light bulb is on. If we reduce the delay, we'll increase the intensity from the light bulb. Let's press the button. Okay, we are reducing the delay. You can see it in the oscilloscope, and the light bulb has a high intensity. We reduce the intensity, we increase the delay, as you can see in this oscilloscope. Okay, let's do it again. If we reduce the delay of the trigger, we'll have higher intensity on the light bulb. If we increase the delay, we have lower intensity, as you can see in the oscilloscope. So the project is working. One button to increase intensity and the other one to decrease. We are increasing intensity. We press the same button to increase intensity. We press the other button to decrease intensity. So this is the digital dimmer. By using two buttons, we can control the intensity of a light bulb. Thank you for watching my project. I hope to see you the next time.